In this section, we're going to look at Parseval's theorem, which is a way to calculate power for a periodic signal in the frequency domain, or that is using the Fourier series coefficients. So we already know we have one method that we've learned a long time ago, which is time domain integral. You take the integral over a period of the signal times its conjugate, or magnitude squared. And that is your power, so that's over one period, and as we go to infinity, we know that the power does not change as we add more and more periods in the limit. But what we're going to do in this section is we're also going to see that we can calculate power equivalently as a summation of the Fourier series coefficients. And we'll see exactly how to do this. Now, the reason that you might want to do this is because it might be simpler. Perhaps a time domain signal has a small number of Fourier series coefficients, and we can do the power calculation on them much more quickly. Or it might be that we already have the periodic signal in that form. And this will often happen in a digital signal processing system where we often work with signals in their Fourier form instead of their time form. So we also call the Fourier form the frequency-based form. So we would say it's convenient if you already have the Fourier series, which in practice we often do. So let's review a couple examples of power for some particular types of signals, and then we'll put it all together to come up with Parseval's theorem. So if I have a sinusoid, so I have, let's say, cosine n omega naught t plus phase. So this would be an example of a term that I would have in a magnitude phase form of the Fourier series. And it has amplitude A. And now I want to calculate its power. Well, I would square the signal. And since these are real numbers, I can simply square them this way to get magnitude squared. And I would then take the integral over one period. And we know from properties of integrals, from a few simplifications, that I get amplitude squared over 2 because I'm taking that sinusoid over n periods. So n is an integer, 1 or more, and I go through n complete periods, and that does not change the fact that the power is amplitude squared over 2. So that was one of the integral properties we saw earlier in the chapter when we were deriving the Fourier series. If I have a complex signal, say a complex exponential, which would be, for example, a to the a times e to the j, and I'll do the corresponding signal here, also called the analytic signal, that corresponds to that cosine over on the left. I take the same phase term, which is n omega naught t plus phase. And now for this signal, I ask, what is its average power? Well, I need to do the integral over one period. And I take the integral of the magnitude squared. So the magnitude is going to be a times 1, because the magnitude of the complex exponential, e to the j times any real number, is 1. Square that, and I end up with absolute value of A. A is a real number, could be a complex number actually, but we'll assume it's real here, squared, because I've integrated over t0 seconds and then I divide the t0 out. Notice this is double what I had for just the cosine. And similarly, if I had a sine instead of the cosine over on the left, I would still have amplitude squared over 2. For our next example, in a Fourier series, let us have two cosines at different frequencies added together. So here we will have C sub n cosine, and our multiple here will be n. So frequency is n omega naught t plus some phase. And we will add that together to a signal that has a different frequency component, C sub m cosine m omega naught t plus an associated phase shift term. Now, if we take the power of this, we still have that the fundamental period of the signal in this Fourier series is t sub 0, which is going to be a multiple of the shorter periods of each of these signals, assuming n and m are greater than 1, but they could be 1. We just have that n is not equal to m here. If n and m are equal, well then we just have a single cosine with an amplitude cn plus cm. So only the case where n is not equal to m is showing us something new here. So we want to figure out the power of this signal here. So what we will do is we will take the integral, but we're going to divide it up into 3 parts. So first of all, let's square the expression. So we have the first and the last term. So we have cn squared cosine squared of n omega naught t plus a phase term. Then we have c of m squared cosine squared of m omega naught t plus a phase term. And then we have the cross term, 2cn cm cosine of n omega naught t plus the phase cosine of m omega naught t plus the corresponding phase. So we break this into 3 integrals and we sum them. Now, the integral over on the right is going to go to 0 and drop out. This is one of the properties that we had earlier in the chapter when we derived the Fourier series. When we integrate over a multiple of periods where each of these sinusoids occurs multiple integer times in there, we showed that the positive and negative areas of that product canceled out, and the area of that integral is 0. So we are just left with the area of the power due to these 2 integrals. And I'm not writing the dt there because we're running out of room. So the first one is just the power of the original signal, the c of n signal. So I'm going to have c of n over 2, c of n squared over 2 for it. And now I have a separate integral for the other one, and I see that's the same integral I would have for cosine at a frequency of m omega naught. So that's going to have power c of m squared over 2. So if we put these facts and a few others together, we will get a way to calculate the power of the complete signal. Remember that x of t in the Fourier series is a0 plus the sum, n goes from 1 to infinity, of the a of n and the b of n with the cosine and the sine terms with frequency n omega naught and time t in each of these. Now, the way we add up power now, is based on each of these A's and B's independently contributing to the power. Now, we showed that if we have two different frequencies, so n takes on two different values, that we can add those powers separately. If we have the A and the B at the same n, we can also add their powers separately. So for each of these terms here, so the power of for x, for each of these terms, n is 1 to infinity, we're going to have a of n squared b of n squared over 2. Now, if that's for the same n, so we add the powers for the cosine component and the sine component. One way to show that that is valid is we know that if we shift the phase of a sinusoid that has the corresponding cosine and sine contributions, we will get an amplitude that is the square root of the sum of the squares. That's a trig identity for that. And so if we just square that, then we are back to a of a sub n squared plus b sub n squared. In a signal sense, we would say the cosine and the sine are orthogonal. And there is a property toward the beginning of the chapter showing that even if n is the same, the cosine and the sine, if I take their product over a period, I get no area. So and since I get no area in the magnitude of the product in the power integral, that means I can add the powers, which is what we're doing here. I also have the power due to A0, and that one does not get a division by 2 for that DC component. So there it is for the sine cosine or trigonometric form. If I put power into if I put the series into the magnitude phase term, the phases don't have any effect on the power. I still have my C0 term, and I still have my n going from 1 to infinity. And now I have my C of n squared over 2 for each of these. Remember, C of n squared is A of n squared plus B of n squared is the relationship between those Fourier series. So this is consistent. Finally, if I am in the the complex form, I have a even simpler expression. My sum now, just like in the series for the complex exponential form, is going to go from n is negative infinity to infinity, and we just have x of n times x of n conjugate, or equivalently magnitude of x of n squared. There are no 1/2s here. The 1/2 goes away because I have the positive and the negative frequencies here, and this is a consequence of Euler's formula. So now, when you are presented a periodic waveform and you have its time domain expression, a function of time, and you have also calculated or have been given its Fourier series coefficients, you can choose either the original method we learned by integrating over time to calculate its power, or you can use one of these three formulas to get its power much more quickly, in many cases, directly from the coefficients. This is especially convenient if the number of coefficients is small and we don't have as many things to add up.